let's do some more problems. Just kind of example problems. I'll probably go off on a tangent at some point in time. We'll go, this is like an 8.5 out of 10. I'm not going to call it quite a 9 because I mean I can get really jacked up with this stuff. But let's say we're approaching like this is about as hard as we get on the test. Approaching. We won't take it up to 11. We won't do that. Maybe an extra credit problem. So if I shun you, I'm kidding. We'll leave you alone with the 1 over x. All right, here we go. Here's our limit. And what's different about this type of limit than the other ones? I mean, look at it. What's it not have? It's not a rational function. There's no x's in there. So if you're to think of plugging in infinity, which you never can do, don't plug in infinity into anything. You can say something tends towards it. The limit is infinity, which is still even misspeaking. Don't plug in infinity. So what I'm about to do is like really against the rules, but we're thinking like, it's not right, just to get the concept. So if we were thinking we're just going to plug infinity in for x, we're like, it's infinity squared plus 7. That's infinity, right? That's infinity. So off on the side, I'm going to be like big old frickin' quotes here. No. And then we're like, there's a minus sign in the center. And we're like, well, what's this? If you were to plug in your infinity over here, you'd be like, oh, so this is infinity minus infinity. All right. When it's infinity minus infinity, that doesn't mean anything. Don't write down 0. Sadly, the answer to this problem is 0. But not always. And in the next problem, we'll have the same case, and it won't equal 0. So infinity minus infinity means do more work. This is what it means. Do more work. Do not just state it equals 0. Sometimes it equals 0. Sometimes I'm going to write it off on the side. Infinity minus infinity, put big quotes around it, can equal 7. Sometimes infinity minus infinity can equal negative infinity. Sometimes infinity minus infinity equals infinity. Sometimes infinity minus infinity equals 1.34. Okay, we don't know. It's like, it's basically the same sort of probability of just saying like, pick a number. Just pick a number. You got about the same probability of choosing what the answer is going to be, except 0 does pop up a little bit more. But trying to get the point across, it's not always 0. Do not write down that infinity minus infinity is equal to 0. You are basically saying chair minus cat is equal to 0. They're concepts. This is not a number. Don't state that. This is just a thought. There's different sizes to infinity. Did you know that? There's different sizes to infinity? Man, infinity messed with my brain when I was a kid. The whole the concept of infinite just really bothered me. Like church and shit like that. You know? Always been there. No start, no end, that sort of stuff. Like, infinity hurts. Okay, moving on. So nowadays I just think infinity, really big, really small, something like that. All right, so let's do our problem. What we want to do is create some sort of fraction. That's the difference between this problem and the ones we've done in the past. So let's create ourselves a fraction by multiplying by its conjugate. Now try not to screw up the signs here. Plus, I got it. Paying attention. All right. And now we're going to bring it in, and hopefully we've seen this step enough times, and we use this a lot, so get good with this. Our denominator is going to be our square root of x plus x, and then up top, so it's going to be, there's our a minus b times our a plus b, so it's going to be x squared plus 7 minus, and then we square up our b, and that's going to become x squared. Oh, cool. Well, I used parentheses on the first one, but I didn't actually need it, so I'm going to take that off. And then we look and go, oh, dope. X squared just cancels straight away. That's good news. It's like this problem's all cooked up to work out super nicely. So then we're just left with a 7 up top. And we got our x squared plus 7 underneath that radical plus x. Can we see where it's going? Can you see where it's going? It's going to 0, isn't it? It's absolutely going to 0. You got x's down below, but you got none up top. But we're going to play that game, and we're going to say we're just going to follow it all the way out. Oh, don't look at that one yet. Follow this one all the way out and say the degree of the top is nothing, but we don't care. It's just the degree of the bottom. So we're going to say it's 1 over x and 1 over x. But this 1 over x is the same thing as 1 over x squared as well, right? Or the square root of 1 over x squared. That's the same thing. Because we're going to have to put this in both places. Look, there's two different places in that denominator it's got to go. One has an x, and one has that root inside with an x squared inside. So those are the equivalencies. They're the same thing, and you have to know the difference, or they're the same, and know how to bring it in to where you're going to bring a square underneath the radical, but you're just going to bring the x underneath the x. So you're going to get the 7 over. And we're going to bring that x in. Bring it underneath here. X squared under there. X squared under there. And just an x, because that's outside of the radical. And we're going to see this is absolutely going to 0. We were just making sure that we got our denominator to not be 0. This is really kind of unnecessary at this point. It's kind of easy just going to 0. Look, there's x's, but I'm going to keep going just because, well, oh, I'm the teacher. I can, I guess. And now we have the radical of x squared over x squared. That was 1. Plus 7 over x squared plus 1. So that goes to 0. So the top goes to 0 and the denominator doesn't. That means it's 0. All right, because you still have I'm going to write it in. Top is 0, and you have the square root of 1 plus 1. So it's 0 over 2. Just confirming the denominator doesn't equal 0. And boom, there's your answer. There's your answer. 0. So from that time, in that particular case, infinity minus infinity equals 0. Let's go to our next. This case isn't going to 0. It's a little bit different. Same idea here, right? Look, you plug in, you get an infinity-ish, huh? Like an infinity minus an infinity, telling us we better do more work. You see infinity minus infinity, and you're like, I need to create a frickin' fraction. You see infinity minus infinity, you think, I need to create a fraction. Infinities like fractions. That's how we make things go away, because I'm not sure if I've ever shown you this before, but this is what makes them go away, the 1 over x, this frickin' limit thing. This is the whole game. Sorry, I went back to it. I couldn't help it. Okay. So let's hit it with that conjugate again. So now we got x squared and it's plus 5x plus x. So it's the same game we just did before. Like, they're the same shit. Cool. So we got our limit. Its x is tending towards infinity. We get it. Sorry, I'm going to just kind of hustle because it's the same stuff we did last time. And then the top is going to become x squared plus 5x. And then we're going to subtract out x squared. Same game. A minus b times a plus b. Set it up. The x squareds go away. But uh-oh, now we have the same degree up top as we have down below. We got a 5x left up there. And then we have the square root of x squared plus 5x down below plus x. Now this is a pretty typical problem I put on tests. This is a pretty typical problem. This is, I go hard when it just comes to like just evaluating limits and doing things like this. Not as much the conceptual, which I need to work on, but you'll know this is something that I like to test on, or maybe throwing a log in there. Maybe having to do the log and bring the limit inside or something. So let's do the same degree. We've got the same degree up top as we have down below. It's 1 up top, right? X to the first. This is x to the first, and then half of 2 is 1. That's since it's underneath the radical, so our degree is 1 top and bottom. So we'll do 1 over x, and we'll do 1 over x. But remember, this 1 over x is the same thing as the square root of 1 over x squared. So we're going to bring that underneath that radical, and let's see what happens. We get the limit as x tends towards infinity. We got our 5x up top. Square root. And then let's bring that x. So anywhere not inside the radical, we're just going to bring an x. Anything inside the radical, in there, we're going to bring it an x squared, not an x. We continue on. Those x's go away, just leaving us with a 5 up top. Those went away, leaving us with a 1 plus 5x over x squared. That's 5 over x. And then x over x, that's just 1. We take this to be 0, and what does that leave us with? This leaves us with 5 over the square root of 1 plus 1. So that's what? 5 over 2. And there it is. Oh, shit. Did you know that sometimes infinity minus infinity equals 2.5? Because it does. These are some tricky ones. Make sure to play around with the one with the natural log. I like that one too. That's in your homework. So you're going to need to bring your limit inside the log and use some log rules. Log rules first, then bring it in. But that'll be the game. So I think I've shown you all the little different tricks and stuff. Yeah, I'll see you soon.